Hello and welcome back. In this lecture, I want to begin discussing a new topic called simple harmonic motion. But before we begin talking about simple harmonic motion, I need to introduce a new type of force, and that is the force that is exerted by a spring when the spring is either stretched or compressed. And the formula for this force is given by this equation right here, which is called Hooke's law. And what Hooke's law says is it says the force that the spring exerts when it is either stretched or compressed is equal to a constant times the distance that the spring has been stretched or compressed. So basically what this is saying is it says the more and more you stretch a spring, the larger and larger the force that spring will exert. Now this constant that appears in this equation is called the spring constant. And what the spring constant is it's basically a measure of how stiff the spring is. So if you have a really stiff spring, something that's made out of a real thick piece of metal, then this spring will have a very large spring constant. So what this means is that if you stretch the spring by even a small amount, that spring will exert a very large force, because we'll be taking this small distance, we'll be multiplying it by a very large spring constant. On the other hand, if you have something like, say, like a slinky, that has a very small spring constant. So when you stretch a slinky, it exerts a very small force. Now before I move on, I want to take a little bit of a closer look at this and figure out what the units of the spring constant are. So Hooke's law says that the force that the spring exerts is equal to the spring constant times the distance the spring has been stretched or compressed. Now recall that anytime we have an equation like this, we know that the units on both sides of the equal sign have to be the same. So this means the units of force are equal to the units of spring constant times the units of delta x. So the units of my spring constant have to be equal to the units of force divided by the units of distance. So one way I could express this is I could say my spring constant has units of newtons per meters. And most of the time, I'll use this as my units for the spring constant. And I'll write the units of the spring constant in this way because I feel that this is a very intuitive way to think about the units, right? This is the number of newtons that the spring will exert when I stretch the spring by 1 meter, right? So it's the newtons per meter that the spring will exert when it's stretched by, some amount. Now, in some later videos, we'll want to actually express the units of the spring constant in terms of the base units of kilograms, meters, and seconds. So remember that force is equal to mass times acceleration. So this means that the units of force, or newtons, has to be equal to kilograms times meters per second squared. So the spring constant has units of kilograms, meters per second squared, divided by meters. So we see the meters cancel out. That leaves us with kilograms per second squared. So this is another way that we could write the units of the spring constant. Now I want to talk a little bit about this minus sign that appears in this equation. Now recall that anytime you multiply a vector by a negative number, it switches the direction of the vector. Okay, so what this means is that the force that the spring exerts is always going to point in the opposite direction as delta x. Okay, so to kind of give you an idea of this, here I've drawn a picture of a mass that's attached to a spring. And I have this little gray dashed line here on the left. This is showing you where the left side of the mass is. So now I want to look at what happens if I move this mass to the left. So if I push the mass to the left, then delta x points to the left. Right, so here's that dashed line, and now the mass is to the left of this, okay? So because delta x points to the left, this equation here means that the force has to point to the right. That's what that minus sign means. That minus sign means the spring force points in the opposite direction as delta x. So if I push the mass to the left, the spring is going to exert a force that points to the right. Likewise, if I were to stretch the spring, so I'm going to pull on the mass, so I'm going to move it to the right. Well, in this case, because I've moved the mass to the right, delta x points to the right. Okay? And the spring force always points in the opposite direction, so my spring force is going to point to the left. Okay? So if I pull the mass to the right, the spring force points to the left. And If I push the mass to the left, the spring force points to the right. So the spring force is always pointing in the opposite direction that the spring has been stretched or compressed. So what this means is that the spring force is always trying to return the mass back to its equilibrium position. And because of this, we sometimes call the spring force a restoring force. So a restoring force is any force that tends to want to return the object back to its equilibrium position. So let's go ahead and look at a couple of examples. The first example says, a car is hauling a 92 kilogram trailer which is attached to the car by a spring, which has a spring constant of 2,300 newtons per meter. And the problem asks us to figure out how far the spring will be stretched when the car accelerates at a rate of 0.3 meters per second squared. Now, before we start solving this problem, I want to point out that when we're looking at this problem, we need to consider what this problem looks like from an inertial reference frame. So in other words, we want to consider what this looks like as seen by a person who's standing on the side of the road. And a person who's standing on the side of the road sees this trailer accelerating to the left. And that person sees the force that's causing the trailer to accelerate to the left is the spring force that the spring exerts on the trailer. So this means there is no force that is exerted to the right on this trailer. Okay? There's not a force that's pushing to the right or pulling to the right. It's causing the spring to stretch out. The spring is stretching out because of the force it exerts on the trailer. So let's start by writing the known and unknown variables. So we were given the mass of the trailer was equal to 92 kilograms. The acceleration of the car is 0.3 meters per second squared. And the spring constant is equal to 2,300 newtons per meter. And what we were asked to solve for is delta x, the distance that the spring is stretched. So since the only force that is causing the trailer to accelerate is the spring force, Newton's second law tells us that the spring force has to equal mass times acceleration. So using Hooke's law, we can write the spring force as minus k delta x. So we have minus k times delta x is equal to mass times acceleration. Now at this point, I know all of these variables except for delta x. So solving for delta x, I see delta x is equal to minus ma divided by k, which is equal to minus 0.012 meters. So I want to talk a little bit about this negative sign. So what does this mean? Well, if we go back to this problem, this trailer was accelerating to the left, and I considered my acceleration to be plus 0.3 meters per second squared. So this means that the positive direction points to the left in the direction that the trailer is accelerating. So when delta x is negative, it means that the spring is being stretched to the right. Okay? And of course that's what we expect is going to happen. The spring is being pulled to the right because the trailer is moving, accelerating to the left. So let's go ahead and look at one more example. This example says a 10.1 kilogram board is wedged into the corner and is held in place by a spring, as shown in this figure down here. Now the board is inclined at an angle of 50 degrees above the horizontal. And the spring constant here has a spring constant of 176 newtons per meter. So we're asked to figure out how far the spring has been stretched. So recall that whenever we have something like this, where we have a board that's in equilibrium, this means that the sum of the forces on the board is equal to 0 newtons, and the sum of the torques is also equal to 0 newton time meters. So we'll be using this second equation here to figure out what the spring constant is going to be. So let me go ahead and open up a blank screen here and just draw another picture of what we're looking at. So actually let me just draw the board. So we have this board here. And the board is at an angle of 50 degrees. And there are two forces that are being exerted on this board. There's the force due to gravity that points down, and then there's the spring force, which, as shown in the picture there, is pointing to the left. So these two forces are exerting a torque on this board. And notice that the two torques tend to point in opposite directions. So for example, the force due to gravity tends to cause the board to want to rotate in a clockwise fashion, whereas the spring force tends to cause the board to rotate in a counterclockwise fashion. So this means that the two torques have opposite signs, and the two torques need to be canceling each other if the board is going to be at rest. So this means that the torque that's caused by the spring needs to have the same magnitude as the torque that's caused by gravity. Now remember, there's a lot of different ways we can calculate torque. One way is we could say it's equal to the force that's perpendicular to the lever arm times the length of the lever arm. Another easier way to do this is we can say that this is equal to the magnitude of the force times the magnitude of the lever arm times, oh geez, I can't remember, is it sine or cosine? Let's see, it should be biggest when it's 90 degrees, so that means it should be sine of the angle between them. Okay, so looking here, if this angle in this bottom corner is 50 degrees, then the angle between, right, so L, let me go ahead and draw this. So my lever arm looks like this for the gravitational force. So that's my lever arm, okay? So my lever arm points like this, gravity points down like this, so the angle in between these two things is this angle up here. So if this angle is 50 degrees, then this angle up here has to be 90 degrees minus 50 degrees, so the angle up here is 40 degrees. So the torque that is exerted by the gravitational force is equal to the gravitational force times this length right here, which is the total length of the board divided by 2. So I'll call that L divided by 2, times sine of 40 degrees. And this thing has to equal the torque that's caused by the spring force. So the torque caused by the spring force is the spring force times the length of its lever arm, which is the full length of the board, times, and in this case, the angle between my lever arm and the spring force. All right, so we have these two things are parallel, so this angle here has to equal this angle up here, so it's going to be the force of the spring times the full length of the board times sine of 50 degrees. Okay, so once we do this, we can immediately see that the length of the board is going to cancel out. And what I'm solving for is delta x. So I need to use Hooke's law here to rewrite the spring force in terms of k and delta x. So we have k times delta x is equal to, k times delta x times sine of 50 degrees is equal to, and the gravitational force is mg, so we have mg divided by 2 times sine of 40 degrees. Now solving for delta x, we see that delta x is going to be equal to mg divided by 2k times sine of 40 degrees divided by sine of 50 degrees. And plugging all of this into a calculator, we see that this is going to be equal to 0.236 meters. So that's how far the spring was stretched. So at this point, I think I'm going to end this video, and in the next video, I want to talk about what type of motion we expect to see when you stretch or compress a spring and then you let go.